everybody. This is the continuation of the lecture that I started a bit before on kidney. That I just wanted to get this taken care of. It's not going to be terribly long this morning. Just wanted to get it taken care of. And this is where we left off. And I did stop here by intent because the juxtaglomerular apparatus is kind of tricky to understand. It's kind of how we auto-regulate our blood pressure, and particularly having to do with how much blood flow we're leaving into the glomeruli, because that makes filtrate, and filtrate ends up making urine. And so if we have too much fluid in the system, read that as high blood pressure. We get rid of it. If there's not enough fluid in the system, read that as blood pressure is going too low. We retain fluid. And so that's what it's doing. And it basically does it in two ways. It adjusts water balance and based on pressure. So it's got pressure sensors and it has chemical sensors. The chemical sensors are for salt, for the salt content of the filtrate. And this is really where the renin, angiotensin, aldosterone mechanism that's we have to have in order to function. Okay. And it has to do with that nephron loop. The nephron loop has a skinny bottom end, but a much thicker ascending end. So the descending end is thin. The ascending end is quite a bit thicker. And where it does, it makes contact, or at least in close proximity, okay, to both the afferent and efferent arterioles. And so at that point, okay, we have in the ascending limb, we have a chemical sensor, and it's called the macula densa. Okay, macula we see in the eye, but this is different. That's macula lutea. This is called macula densa. Don't get them confused. Fortunately, we're not doing eye anymore, but that's something you have to be wary of. And that is a sensor for salt content. So basically, if it's too salty, then probably we have to retain fluid. If it's not salty enough, then we probably have to get rid of fluid. Think of it that way, because it's measuring whether, it's almost like that idea of isotonic, hypotonic, hypertonic. The juxtaglomerular cells, okay, means they're close to the glomeruli, and they're smooth muscle cells on the afferent arteriole. And they're pressure sensors. They effectively are stretch receptors. And in between them, you have specialized cells that run. So here, you can see this macula lutea, chemical sensors. And here you can see the juxtaglomerular cells lying within here. This is called the juxtaglomerular apparatus. And in between the two, and you don't see them there too much, at least in this diagram, are little messenger cells. They call mesangial cells that basically communicate with one another. And how you know this is an afferent arteriole, and these are really wonderful illustrations, by the way. An afferent arteriole, it's wider than the efferent arteriole. So that's by design. So this is much more adapted to high pressure. This is much more adapted to regular or lower pressure. And what happens here is that this is eminently adjustable. So if we need to increase flow, we can increase it and relax these. There's a lot of structures here, smooth muscle that can relax. And by the same token, if we have to decrease flow, we can narrow these. And by the same token, we have the same capacity here. So imagine we really want to maximize the amount of fluid that's going to eventually be filtered through this unique apparatus and start its merry trek through the proximal convoluted tubules and the nephron loop, et cetera, all the way up into basically making urine. Is you could widen this and to some extent narrow this, and it stays longer in here. And as long as it's sloshing around in here effectively, you're making filtrate, and eventually that means making more urine. That's why it's such an important area. And so the way it does when its pressure is low, it can do things like that. When the pressure is low, it can restrict. Okay, think of it this way: it limits the amount of flow. So it'll narrow this, it'll widen this, do the opposite. So basically, blood gets through there faster, and it minimizes the filtrate and raise blood pressure. At the same time, inside there are. The best way to describe these juxtaglomerular cells is they have the capacity to make tiny little droplets of a chemical called renin. That's the catalyst for this very famous reaction. So we're going to get farther into that down the road. I'm going to do that on the board tomorrow, which is Friday. I'm doing this one this dictation this morning, which is the Thursday morning part of it. These are different things. Glomerulonephritis can be a lot of things that cause this to occur. I mean, it could be infection, but classically, it's immunological. And we've talked about this, and I do it with my micro, perhaps in your micro, beta hemolytic streptococcus, which is Streptococcus pyogenes, the good strep throat strep. It causes these antigen antibody complexes, which clog up the glomeruli, and because of that, the kidney shuts down. That's the kidney's response to everything. And this can be chronic in nature unless it's addressed. How would you address it? There's a variety of ways. Basically, increase the amount of fluids that, trying to get it right, to some extent, I don't want to overstate it. It's certainly not going to be a question unless I know for sure what the current treatment is for acute glomerulonephritis. In general, you're trying to do a certain amount of fluid management, and effectively by treating the streptococcal infection, you reduce the number of antibodies. So I can't give you the specifics, and what it will do, you probably have to be very cautious with fluids, because if you overload them, there's a problem. So once urine starts to flow again, and it typically will, then good things kind of happen after that. And I guess if it's a prolonged inflammatory from infection or some other unique process, much larger problems. And what comes out of all this is urine. And basically, it's water, effectively excess, and there's always a certain amount of water just to keep everything dissolved in liquid phase so it'll pass properly. Okay. And at the same time, you got waste products, you have electrolytes, just basically, and these are the three processes that are famous, called glomerular filtration, tubular reabsorption, and tubular secretion. Filtration is just that. Okay. We filter, and basically that develops this thing we call the filtrate. Larger, basically formed elements, red cells, white cells, platelets, and proteins can't get through. Everything else can. It's all anything that effectively is dissolved in the plasma can get through, with the exception of proteins, which are often dissolved in the plasma, and the formed elements. Okay. At that point, it's processed. So this filtrate is 99% reclaimed, and most of it is done by a combination of reabsorption and secretion. The vast amount of this is done in the proximal convoluted tubule. Most of the urine is taken care of early, 2/3 of it probably. And it pulls stuff back that we need. So think of the stuff that's dissolved in there that we use all the time: amino acids, glucose, a variety of things that are building blocks for cells. They're all basically reabsorbed. On the other hand, we start to secrete stuff we want to get rid of: excessive ions, like excessive potassium, which is a problem, excessive, acidity, and sometimes even bicarb, all that types of stuff. A variety of things are pushed out, including things we have talked about previously, those nitrogenous wastes like uric acid and urea. And it's interesting that even sometimes we even reclaim the urea just for a little bit to create a gradient, to create, it's almost like, hey, we have extra urea, let's use it and push stuff out. And really the big player around this for moving stuff in and moving stuff out is sodium, because we actively transport that back in, and at the same time we cause some stuff to be co-transported and some stuff to be shipped out by something called anti-transport. It's a neat process. We don't go into the details. And so that's what it is. So most of this occurs here, but if you want to paint with a broad brush, the major action that is in, even though both occur, the major action is reabsorption in the proximal convoluted tubule. And certainly the major action, because it's like the finalizing the urine, is secretion in the distal convoluted tubule. And the loops are all about basically concentrating the urine. And they're just showing you, different kinds of pressures, which we're not going to get into effectively. And basically here you can see the greater blood flow. It goes through here, and all this filtrate begins to work its way. And so what we begin to see here with the absorption, it's a good way to illustrate it. Now these are called the peritubular capillaries because they're around the proximal and distal convoluted tubules. Now all the stuff that's being either reabsorbed or secreted is taking place there. That requires the energy. That's that sodium active transport. That's the transformation accurately here from arterial blood, because it didn't change, even though it went through that capillary bed to venous blood. Okay, that's that. So substance is moving, and this is just the filtration into the capsule. Water and small dissolved molecules. This is exactly what's there. This is the stuff. I would say proteins in general. I think without going crazy about the size, because there's if it's tiny proteins, they're probably more in the line of polypeptides. I really don't think that's accurate, and I wouldn't ask you about it. They have the fenestrate or fenestrations, the tiny little openings. The filtrate forms, and filtrate has very similar to tissue fluid. Here it comes running through, all the stuff's going out of it. I mean, again, these are really good illustrations to show you what's happening. You don't have to really go crazy about this. The main force is pressure. Okay, high hydrostatic pressure. The afferent arteriole, again, larger in diameter than the efferent. Resistance in the efferent arteriole increases blood pressure in the glomerulus, which favors filtration. And because the outflowing is a little more narrow, in other words, it can't just rapidly flow through the glomeruli. It's kind of pushed back a little bit, and the more it does that, rolling around, so to speak, the more is contained within that capillary bed, the more filtrate that's going to occur. And really, this is a comment of your blood pressure and why we need that wide artery coming in creates the hydrostatic pressure. And again, there's plasma proteins, there's pressure there, okay? And it's all about net pressure. So there's forces that oppose it as well. So there's things that are holding on. And this is what happens all the time. You have proteins and other things we call colloid osmotic pressure. Remember, we had talked about that ages ago. Proteins in the bloodstream, is when we talked about the blood, like albumin, they hold on to water. So you have the blood pressure or the power pressure pushing it out, and you have the colloid osmotic pressure, the protein pressure holding it in. As long as there's more pressure pushing it out than holding it in, you're going to have positive filtration pressure. It's going to filter. And this is just showing it to here without doing it. It ends up they crunch the numbers. Okay, you got 60 pushing it out. You got about 50 trying to push it back in. There's pressure in the capsule. There's pressure from the proteins holding it. But still, net effect is out it goes. It's a good way to describe it. We had talked about this. 25% typically on average throughout the day of your cardiac output goes to the kidneys. 20% of the blood is filtered by the capillaries. It's amazing. This is a really important number, 125 milliliters per minute. And this is an important 108 liters a day. What it means is if you think there's typically 6 liters of blood, your blood, the entirety of your bloodstream is going through your kidney 30 times a day. Think of that. Okay. And this is an important number because GFR, which stands for glomerular filtration rate, that's the number we look at to see if kidneys are in trouble or starting to fail or are failed or you're going to have to be on dialysis. So 60 times a day worth of plasma. Remember, it's not all. Okay. When you do the 20% of the blood. But you can imagine it's just a massive, massive, massive volume. You mean to do that? Let me back up. Just a massive, massive amount of volume that's there. Only a small percentage of filtrate is excreted. You can see about 1% average, plus or minus. So all this is proportion to all of these factors that are there and the different change in diameter. That's what we were talking about before with that juxtaglomerular apparatus. It does all these things. It really plays with the diameter more than anything else. And there's other ways that the renin-angiotensin aldosterone mechanism does. So here you can see it. Typically, for most of us, depending on really how much blood you contain, there's a vary, but it's usually typically between 160 and 180. This is sort of the ball game. So there are days when you just don't go a lot. And there are days, boy, I can't seem to stop going. And effectively, that's what it is. There's so many different factors. So we were talking about that juxtaglomerular apparatus is autoregulation. So you can see when your blood pressure goes up, we narrow that afferent arteriole so it doesn't overload it, okay? Limits the amount of flow that's going in, so to speak, causes vasoconstriction of that incoming arteriole for protection, reduces the blood flow, decreases the filtration, and maintains it. So it's just trying to keep that relatively constant. Okay? So you're not trying to damage the system. It's so complicated. And so increased GFR increases the amount of filtrate, excess sodium reaches the macula densa. Then what it does is it basically, if there's excess sodium, now it's going to constrict those afferent, and remember the afferent are the incoming ones, to keep it in the normal range. So there's lots and lots of different conditions. I'm not asking you to be able to say, well, there was more sodium, and now what does the JGA do? I don't do that with the advanced classes. Like I said, kidney is very, very difficult to work with. So there's lots of different things. For instance, there's a lot of different conditions that can do this. But effectively, remember we talked about mean arterial pressure. That means roughly, and as long as it's roughly between 80 and 180, that's an enormous range. Most of us are around 93, 95, maybe a little lower. As long as you're in that normal range, oh my goodness, you don't have to worry about anything with the blood pressure. And that's a vast range. Even people with high blood pressure, people who want 160 over 110, just picking numbers off the top of my head, that would be a mean arterial pressure of 120. Your kidneys can still take care of it. Mind you, over time, that causes real stretch problems with all those little arterioles. They gradually become damaged. They start to scar. It's not as efficient, and it's sort of a vicious cycle that happens. We had talked about atrial natriuretic peptide. There's also a ventricular natriuretic peptide that basically, when the atria or the ventricles are switched, or bigger part stretched, they will cause more sodium and therefore more water to be excreted to normalize it. And certainly the sympathetic is the big override. Remember, parasympathetic doesn't do anything here because sympathetic controls blood vessels. Parasympathetic doesn't impact the kidney, let's say, directly. What sympathetic does is it controls the diameter of blood vessels. So response to those changes, when blood pressure volume decreases, again, it can basically cause the constriction that occurs there. It's all about maintaining it. And then we're going to get into renin-angiotensin mechanism. And really, this is the formal name, renin-angiotensin-aldosterone mechanism. Whenever there's a subtle fluctuation, it gets a little bit low, and we're doing it all the time. Okay, it could be decreased blood pressure, sympathetic stimulation, or something that impacts the macula densa, the salt sensors, decreased salt concentration. Renin converts this angiotensin 1. I'm going to do this on the board again. It's converted angiotensin 2, and there's something called ACE, which is angiotensin converting enzyme. And these are important for many of you to understand going forward, because this is one of the critical pathways that we control blood pressure. We stopped controlling blood pressure years ago by diuretics. We still use them, but not routinely. This is when the things that work are called, because they're easier ways to control it. The problem with the diuretics is it really impacted lifestyle. You're constantly running to the bathroom. On the other hand, like what I take medications that impact these pathways differently. Okay, I have a calcium channel blocker. I have something called Cozar. Okay, and they have impact within the structure of these pathways. So this has been a real change in the way blood pressure medicines have been used over, let's say, the last 50 years. So these are now go-tos. And as you'll see, the angiotensin 2, which is the active form, as its name suggests, squeezes the blood vessels. That's going to raise blood pressure. Okay. Increases antidiuretic hormone, makes you thirsty, so you drink more. Antidiuretic hormone pulls more water in, and moreover, and most importantly, aldosterone, which basically forces sodium to be retained in the kidney, and water follows it. So all of those are the main features of that mechanism. And we'll look at it. You don't have to go through all those. I'll come back and we'll look at this renin-angiotensin aldosterone mechanism, because it's a very good illustration. So renin-angiotensinogen is the inactive form. That's always in your bloodstream. Renin changes to angiotensin 1, which has some limited activity. But when it gets to the lungs, okay, the angiotensin converting enzyme makes it active in angiotensin 2. And as you can see, vasoconstriction, Antidiuretic hormone, increased thirst, and eventually it goes all the way and triggers the adrenal glands. And the largest portion of the core of the adrenal cortical gland, so to speak, that outer portion makes aldosterone, and it's vital. We have to have that aldosterone working, or we're going to lose sodium. And if you lose too much sodium, you're really at risk. So we have very big numbers of sodium, but we need them. Boy, do we need them. So I think that's a really important thing to remember as well. So reabsorption, useful substances back in. 70%, as you can see, in the proximal convoluted tubule, has microvilli, has a lot of mitochondria. Again, microvilli are what? Surface area. Okay. And different areas. And so substances can just diffuse back in. Remember, lipid soluble, they get through the membrane. Osmosis can move water in. But this is something we have to deal with a lot with, is active transport. I'm going to stop it here because I really need to explain transport maximums and thresholds. I think that's important. Nephrotic syndrome, the whole idea of sodium and water, at least to give you some background about that. As you can see, typical amount, 180, 99% absorbed. Typical amount of excreted water, 1.8. That's about right. Same thing with, notice the sodium. We filter it, we resorb 99.5%. If we didn't have the aldosterone, it would start to diminish. So we'll look through a lot of these slides that I'm sort of buzzing through without going crazy about it. Because and they've done a very good job, and it gives you, like saying before, and then we'll basically the topic I do want to hit at some length tomorrow in lecture is this countercurrent multiplier. And once we're done with that, we're basically done with the kidney. So thank you very much. I'll flip back out here. Just a second half an hour of lecture, and I'll see everybody tomorrow.